Welcome to the data structures course. Today we will see nonlinear data structures. In that we will see height balanced trees. So first of all, what is the need to have balanced trees? And there are two types of height balanced trees, AVL trees and 2-3 trees. So we are going to look at AVL trees first. So first of all, let us see what is the requirement for balanced trees. So in binary search tree, it gives advantage of fast search. It means whenever we add nodes into the tree, it will be either inserted at left and it will be either inserted at right. So the search space to search a node will be divided into half part. But there is a problem in binary search tree, and it is in worst case, it will give the height which is not near to log n. And what is that worst case? Whenever we have elements which are already sorted in ascending or descending order, then our tree will look something like this. Okay, so if we want to insert node 20, 30, 40 and 50, we have to insert them one by one. First of all, we'll create node 20, then we will insert 30. As 30 is greater than 20, it will be inserted at right and so on. So this tree will look something like this. So what is the problem in this? This is a right heavy tree. This is called a right heavy tree. Means this tree has only right subtrees in it. So what it will do? It will slow the searching process. So it is necessary to divide the search space into equal halves, and that search space into equal halves is only possible if the tree is balanced. If our tree will look something like this, 20, 10 and 30, then in first go we can find this 30. But in this case, if we have tree something like this, 10, 20, 30, then in third level we will be able to find 30. So this is the problem in binary search tree, which can be solved using AVL trees. AVL trees are also called as self-balancing binary search tree. Means it will balance height of the tree by itself. Okay, as we proceed to insert nodes in the tree, it will take care of height balancing. And AVL trees are binary search trees in which the difference between the height of left and right subtree is either -1, 0 or +1. Means the difference of the height in left subtree and right subtree can at most be 1, not more than that. Okay, if the height difference between left and right subtree is greater than 1, then we can say that the tree is imbalanced tree. So the balance factor is known as the difference between the height of left subtree and the right subtree, and balance factor should be within these three numbers, -1, 0 or +1. Okay, so allowed values are -1, 0 and +1, and the value -1 indicates that the right subtree contains one extra node. Right subtree will contain one extra node if the number is minus. Okay, means the tree will be right heavy. If the value of balance factor is positive, then we can say the tree will be what? Left heavy tree. Means a left subtree will have an extra node. Okay, and value 0 shows that the tree includes equal nodes on each side. Means in left and right subtree, the tree is perfectly balanced because it has equal amount of nodes in both halves. Okay, so this is the AVL tree, and we will see the different rotations in AVL trees. There are two types of rotations in AVL search tree: single rotation and double rotation. And these are the four rotation cases in AVL tree. We will see them one by one with the help of example. So what is left-left imbalance? In case when the tree will be left heavy, it will create left-left imbalance, and in that case, we have to rotate the node at right, and that rotation will be at single node. That's why it will be called as single rotation at right. So let us see with the help of example. So we have three nodes A, B and C with us. Okay. So let us calculate balance factor of C first. As C doesn't have any left and right subtree, balance factor will be 0. As B has only left subtree and no right subtree. So balance factor will be height of left subtree, which is 1, and there is no node in right subtree. That's why balance factor will be 0. That's why total balance factor will be positive 1. Means the node B has left heavy subtree. Okay. Then let us calculate balance factor of node A. So height of left subtree is what? 1 and 2. So left subtree's height is 2 and there is no node in right subtree of A. That's why height of right subtree is what? 0. That's why 2 minus 0 will be positive 2. That means this tree is left heavy. But now balance factor is allowed till number 0 and 1 only. If the height difference between left and right subtree becomes greater than 1, means here plus 2 is there. That means the node A has imbalance in it. This is what? An imbalanced node. So this type of imbalance falls under left-left imbalance. Why it is left-left imbalance? Because there is a node which is imbalanced node and that imbalance is due to left's left subtree. That's why it is called as left-left imbalance. And in that case, we have to rotate the imbalanced node at right side. Means we will pick this A and we will pull this A at right. So how can we do this rotation about A? We will pick A and we will pull it at right. So if we pull A at right, we will have A at the rightmost subtree. Then we will be having B as root node and C will stay as it is in left subtree. Okay, so if we rotate this tree at right about A, then we will pick A and we'll pull A at right. So our tree will look something like this. So now the tree is balanced. As again, if we will calculate the balance factors, then balance factor of C will be what? 0, as it doesn't have any left right subtree. A will be also what? 0, and 0 minus 0 will be 0. So now the tree is what? Perfectly balanced tree. So this was the left-left imbalance case. So let us see right-right imbalance. Whenever the node will be imbalanced and it will generate a right heavy subtree, and the node will be imbalanced because of right's right subtree, then in that case it is called as right-right imbalance and we will rotate it at left. So in this case, if we will pick A and pull it at left, so A will be attached at left, B will be attached in root and C will be attached as it is in right subtree. Okay, so this is the balanced tree now. So let us see the special case of this. If we have this tree and in this we want to perform left rotation on B, then we will pick B and we will rotate it at left. Okay, so we will pull B and we will rotate it at left side. So what will be done? D will be in place of root. Okay, D will be in place of root. But what about the left child of D? Whichever node will be put in root, its left subtree will be connected to the new left subtree. Okay, so its left child will be connected in left subtree. So here there is empty place at right child of B. So this left child will be connected in left subtree only. Let us now see right-left rotation. Okay, so this is also called as double rotation. As in this case, we have to rotate the node twice. Okay, so this is the case of right-left imbalance. Here, node A is imbalanced because of its right subtree's left subtree. That's why it is called as right-left imbalance. And we will do right-left rotation in order to balance the tree. So first of all, we will do right rotation. But for which node? We will do rotation. We will do right rotation at node B first, and then we will do left rotation at node A. Okay, so we will rotate B at right first, and then we will perform left rotation at A. So if we perform right rotation at B, if we pick B and pull it at right, then the tree will look something like this. So if we perform right rotation on B, then tree will look something like this. Pick B and pull it at right. So if we will do that, then C will be placed here and D will be placed here. Okay, so this is the first rotation. What is the second rotation? Second rotation is left rotation. Which node has to be rotated left? The node A has to be rotated left. So next step is to rotate node A at left. So if we pick node A and pull it at left, we will have tree something like this. A, C and B. So now this is perfectly balanced tree. So this is first rotation and this is second rotation. That's why it falls under double rotation. Okay, first rotation at right and next rotation at left. Let us see left-right rotation. Here node A is imbalanced because of the imbalance in left subtrees, right subtree. That's why it is called as left-right rotation. Now, what is the solution? First of all, we have to perform left rotation, and that left rotation will be performed on child of imbalanced node. Means at node B, we will perform left rotation. So if we'll pick B and pull it at left, our tree will look like this. A, C and B. Okay, so this was the first rotation, left rotation on node B. What is the second rotation? That is right rotation. That rotation will be about A. So we will rotate A at right. So in this resulting tree, we will rotate this A at right side. Right? So if we'll pick A and pull it at right, okay, C will be at root, A will be at right, and B will be attached in left subtree. So this is perfectly balanced tree now. So this was the left-right rotation case.